So an exponential function is of the form f of x equals some base a to the x power. There are restrictions on what the base can be. That's what your base of your exponent can be. The first restriction is that your base has to be a positive number. So fractions are okay, decimals are okay. It just needs to be a number that's positive and it cannot equal 0. Okay, so if we had a base of 0, then everything would just come out being 0, which really wouldn't be a function. Okay, so when you have an exponential function, we know that the base needs to be a positive number, and this number cannot be 0. So the first thing you're going to have to be able to do is graph an exponential function. So we're going to graph two separate ones. First one is f of x equals 2 to the x, which we already kind of have set up for ourselves, which is nice. So the only way we're really going to do this is by making a quick table of values. It's smart to pick some negative values, it's smart to pick 0, and it's smart to pick some positive values for your domain that you're going to plug in. We already kind of figured these out, so 2 to the negative 2 power we said was what? 1/4. 2 to the negative 1 was 1/2. 2 to the 0 was 1. 2 to the 1 is 2, and then 4. All right, let's try to graph these as best as we can. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So negative 2 and 1/4. Yeah, that's kind of hard to graph. Just kind of eyeball where you think a quarter would be. I'm going to say that it is right about here. Negative 1.5, so maybe right about there. 0, 1, that one's easier to plot. 1, 2, 2, 4. Is it making a line? No. It's making a curve, and when you make your curve, be aware that you want arrows on both ends. And you never, ever, ever want this line to cross that x-axis. You'll get points taken off if you do that. Because remember we said it's never going to hit 0. Doesn't matter what negative number I put in, it's just going to be a number closer and closer and closer and closer to 0. But it never touches 0, it never goes beyond 0. So make sure your line doesn't go below the x-axis. Okay? What if we changed my base from a 2 to a 1/2? Then what would our table of values look like? So if we had to graph g of x equals 1/2 x. So now when we do our table of values, what's my output going to be? What's 1/2 to the negative 2 power? Not 2, you're thinking the right track though. Because you have to square it. So the negative 2 would flip it, right? Flip the fraction. 1/2 to the negative 2. If I could write, negative 2 is equal to 2 to the positive 2, which would be 4. So 1/2 to the negative 1 power would be 2. And we get 1, then 1/2, then 1/4. Good. Okay, so if we plot those, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So negative 2, 4. It's right about there. Negative 1, 2. 0, 1. Eyeball 1.5. Eyeball 2.25. Connect your curves, make sure your line does not go underneath that x-axis. What's the difference between this graph and the previous graph? It's flipped. The values are the same, right? But if we think about left to right progress, is this one decreasing or increasing from left to right? It's decreasing. The previous one was increasing. Where do you think that connection comes from? Right, we'll focus on the base. Here my base is 1/2. The other one, my base was 2. What if my base was 1/3? Do you think it would be decreasing or increasing? It would be decreasing. What if my base was 1/4? Decreasing. What if my base was 5? Increasing. So let's put a statement to that pattern. When your A is what? It's going to be increasing. Well, not necessarily a whole, because it'd be 5.5. Greater than or equal to 1, right? And if it's in between 0 and 1, so it makes it a fraction, is when it's going to be decreasing. So here are some important concepts to remember about graphs of exponential functions. So, when you have just a basic exponential function, your graph is always going to have the point 0, 1 as its y-intercept. Because anytime you take anything to the 0 power, it always ends up being 1. So as long as it's just in the normal form of a to the x, with nothing else fancy happening to the x, it's going to have a y-intercept of 0, 1. Okay. When your a is a number larger than 1, this is the same as increasing, the graph will rise from left to right, just like the first graph that we did, because there our a was 2. 2 is greater than 1, so the graph is going up from left to right. When your a is between 0 and 1, the graph will fall from left to right, so it will be decreasing. The reason why it's not equal to 1, because if it was 1 to any power is going to end up being 1, so that would end up being a straight line, a horizontal line, which would not make it exponential anymore. So when you're greater than 1, our graph's going to be going up. When we're in between 0 and 1, our graph is going to be going down from left to right. Number 4, we talked about this. The graph will approach the x-axis, but it will never touch it. So be very careful. That will be some silly points that you could lose on the quiz and the test. I won't be so picky about it touching it, but make sure it doesn't go beyond the x-axis, because then you will definitely lose points. Because then you're telling me that you don't understand that it's not going to ever touch 0. Okay, so be careful with that. All right, questions with graphing? No? Good. Hopefully we just remember our powers, like 3 to the 3rd power, 3 squared, all that fun stuff. All right, and then we've got our domain and range, which we talked about. The domain already. For any exponential, bless you, any exponential function, our domain is all real numbers. And our range, if we think about the graphs that we just created, they look like this. They look like this. Remember, your range is your y values. So the lowest y value I'm going to get is not necessarily 0. That's why we put a parenthesis here, because it's not including 0, but it's including everything larger than 0 to positive infinity. So your domain, all real numbers. Range is parentheses 0 to positive infinity. All right. Yeah? Good with that? Okay. So we've got our graphing down. So now let's do a funkier graph. See what happens when we change some things. Are we ready? What if I have some other things occurring to my exponent? So if we had f of x is equal to 3 to the 2x minus 4. So it's no longer just 3 to the x power. So is my y-intercept going to change? Probably, right? So if I plugged in 0, I'm going to get 3 to the negative 4 power, which is not 1 anymore. So my y-intercept is going to change. But the process of what we're going to do is not quite going to change. So let's pick some ordered pairs. Let's make a table of values. X, Y. Whoops, come back. So let's go with, let's see what negative 2 looks like. That might be too crazy of a number. If I plug in negative 2, 2 times negative 2 is negative 4. Negative 4 minus 4 is negative 8. 3 to the negative 8 power. It's going to be 1 over something. I don't even know what 3 to the 8th is. Some giant number probably that I don't want to graph. 3 to the 8th power is 6,561. So, would that look like a nice number to graph? No.
Yes.
I don't think so. So we probably don't want to start with negative 2. Is negative 1 going to make it any nicer? No. Is 0 going to make it any nicer? No. Let's just do 0, because sometimes it's nice to see what your y-intercept is. What would be 3 to the negative 4th? I'm cheating using my calculator. 1 over 81. Still getting pretty close to 0. What about 1? That'd be what? 1/9, because it would be 3 to the negative 2, so 1 over 9, a little bit nicer. What about 2?
1.
Yeah, because that would be 3 to the 0, which would be 1. What about 3? That would be 9. All right, so there's some numbers that we definitely can graph. So let's go ahead and plot those. So it looks like I have to go up to 9 on my y-axis. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 1, 2, 3, 1, 2, 3. All right, let's start with 0 and 1 over 81. So 0, 1/81st. I don't know. I'm going to eyeball it. I'm going to say that's pretty darn close to 0. That looks about good. 1 and 1/9. Maybe right about there. 2, 1. That one's a nice dot. I know where that one's going to be. And then 3, 9. Puts us up there. So we can see our curve. It's increasing, which makes sense because my A is 3. I'm going to make sure that my graph does not cross over that x-axis. Okay. So process is not changing. It's just your input values may change depending on what makes it work out the nicest. All right, ready to get away from graphing? Get away from math? No, just graphing in general. All right, so now we're going to solve exponential functions. Now our steps for solving an exponential function for today, we're going to learn different methods on how to do it as we continue on throughout Chapter 11. When we start talking about the inverses of exponential functions, which are logarithm functions. Remember your logs from last year? Hopefully. So, for just today, the equations are going to work out pretty nicely so that you should be able to end up making both sides of your equation having the same base. So if I can make both sides the same base on the either side of the equal sign, then I should be able to solve it very easily. So each side must have the same base. If two sides don't have the same base, we're going to express each as a power of the same base. You'll see what we mean by that in a little bit. Step 2, simplify the exponents if necessary. Once we have the same bases on either side, we can actually ignore those bases and just focus on the exponents themselves and set the exponents equal to each other and then just solve. So now we got to wrap our brain around powers of numbers. Some of them are easier to see than others, especially the fraction ones. Those are a little bit harder to see. Okay, so our goal is, given an equation, can I make the bases on both sides become the same base? And if I can, I want to rewrite them so that they have the same base, which means I'm probably going to have to do something else to manipulate the exponent. And once I have the same bases, I'm going to ignore everything else but the exponents, set them equal, and solve. And that will allow me to be able to solve for x. Okay. Are you ready to see it in action? Okay. Good. All right, first one. 9 to the x equals 27. Looks pretty easy, right?
Yeah.
Well, 9 to the 1 power we know is what? 9. 9 squared is 81. So neither of those is 27. So we know that our x needs to be somewhere in between 1 and 2. It's probably going to be closer to 1 than it is to 2, because 2 is all the way at 81. So we could sit there on our calculator and guess and check some numbers to see what we get to it. So what we can do is we can try to solve this using the process that we just wrote about. So now let's think about this. 9 is my base here. My base here technically is 27, because what's the power on the 27 right now? 1. They're not the same, but is there a number that I can either square or cube or take to the 4th power that becomes a 9 and then 27 at the same time? 3. So if I make those into a base of 3, 9 is really the same as 3 squared to the x equals 3 to what power is 27? 3 cubed. So I didn't change anything about my equation. I just rewrote it. So I could take it from here back to the original. So now let's simplify exponents. What am I going to do with these two exponents? Just multiply. So that becomes 3 2x equals 3 to the 3rd. Now that my bases are the same, I can ignore them and just set my exponents equal to each other, which is nice. So we get 2x equals 3. So x is equal to 3/2, which we said it had to be somewhere between 1 and 2. Little did I know it was exactly between 1 and 2. That would be your answer. So if I typed into my calculator 9 to the 3/2, it should come out to be 27.
Nice.
Okay? So sometimes it's hard to think about what the bases should turn into. All right, let's do this one. 3 to the 2x plus 5 equals 1. That's not complicated. What's my base on the left? The base is 3, right? So that's like the most minimum we're going to get. I can't take any other number to a power and make it become 3. So now I need to think, how can I turn my 1 into a base of 3? 3 to what power is 1? 0, right? So can I rewrite that whole entire 1 as 3 to the 0 power? Sure. So 3 to 0 power, 3 to the 2x plus 5. Now your bases are the same. So just set your exponents equal to each other. So 2x plus 5 is equal to 0. So what's that going to get us for an answer? Yeah, -5/2.
Nice.
If we were to check it. No, you can just leave it like that. I guess we should probably be putting in a set notation. Yeah, I'm not making these fancy enough for our course. Set notation would fancy it up.
Just make Jenna do that.
Huh? Yeah, that one didn't turn out too good. Yeah, because it's your solution set. All of our solutions have been in set notation. All right, let's try this one out together. 4, 3 to the x minus, or 3x minus 1 equals 16x plus 2. What are you thinking? Yeah, so this has a base of 4. What's nice is because this is 16, 16 really is 4 squared. So I could technically take this to 2 squared, and then I could take this technically to 2 to the 4th. That would just be more work than I need to do. So let's turn that 16 into a 4 squared to the x plus 2 power. So what am I going to have to do with these exponents? Yeah, and we're going to have to distribute that. So on the left, nothing's changing. 4 to the 3x minus 1 equals 4 to the 2x plus 4. Now my bases are the same, so set them equal. Your exponents, 3x minus 1 equals 2x plus 4. What are we going to get? X equals 5?
Yes. Nice.
Let's fancy it up.
Nice job.
Put it in set notation. All right, are we ready to throw some fractions into the mix?
No.
Yes, you are.
Oh. You might be right.
Now the fractions make it a little bit more complicated, but we just need to remember with fractions, I'm probably going to have a negative exponent that's going to be occurring. All right. 6 to the x power equals 1 over 216. So the easiest thing for you to worry about is, since that's a 1, ignore that, just focus on the 216. 6 to what power is 216?
Third.
It's to the third. So if I wanted it to be 1 over 216, it would have to be 6 to the negative third power, right?
Wait. How do you get 216? 6 to the
Well, since my base here is a 6, I need my base over here to be a 6. So then I need to figure out 6 to what power is 216, which is 6 to the third power. But since it's 1 over 216, I need it to be to the negative 3 power. So I'm going to rewrite that 1 over 216 as 6 to the negative third power equals 6 to the x. So what does x equal? X equals negative 3.
Noise.
All right, let's make it one step complicated, or more complicated. Complicated, it's not a word. 2/3 to the x equals 9 to the 4th.
No idea.
Well, my base here is 2/3. So that means my base over here needs to be
Do you
2/3.
actually need to change it? So it's something how to get that answer right away.
So let's think about it this. We're going to have to flip it, right? 2 to the 3rd squared is what? 4 to the 9. But I need it to be 9 to the 4th. So if I make it a negative 2, then wouldn't it become 9 over 4? So my 9 to the 4th is the same as 2/3 to the negative 2 power equals 2/3 to the x power. So what does your x equal? X equals negative 2. Good. Your brain doesn't think like that? All right. Questions with any of that? So we've got graphing. Everybody can handle graphing? We've got solving. The last thing you have to do is just a simple word problem.
Oh my god, so much notes. I'm running out of pages.
This is it. This is the last thing. Just write this function down.
Pages of notes.
Carly, I have no room.
Then just watch.
Already.
0.0995 to the x. All right, so you're going to be given an exponential function, and all you're going to have to do is evaluate it. So if we say that this function models the enrollment in a high school where x is the number of years since 2005, Use the model to estimate the enrollment in 2020. Well, how many years is it from 2005 to 2020? 15. So what number am I going to plug in for x? So then it's just calculator work. So then I would grab my calculator and I would type in 2300 times 0.995 to the 15th power, and we get 2,133.4, let's say, people. True. 0.4 people. Well, you're estimating. What? Well, you can move. So 0.4 people, so if you were to estimate, we could say about how many people?
2134.
You would round up? Okay. So 2,134 people in 2020. That's it. The word problems aren't hard. You just have to figure out what value to put in for x. That's it. That's how many years it is from 2005 to 2020. That's it. Okay? All right.